Yeah, let's take this simple uh, example. You have a camshaft here with a cam mounted on it, and there is a follower which can move along this direction only. And naturally, it is supposed to trace the profile of this cam, whatever is the profile. Some arbitrary profile has been shown here. So this follower is going to just follow the profile of this cam. In the process, it is a velocity or a motion is being imposed on this end, on this follower. So it will move with the velocity v1. Okay. And on the other side, you have the mass. Okay. Of course, we could have had a little more detailed version of this, more elaborate version. I have not shown the constraints over here. We can also bring in the constraints. Okay. So here you have um, this going in and out, and also this mass. So this mass has been shown. So the velocity of this mass is shown here using this one junction. You assign the inertia of this mass over here on this one junction because it moves with the same velocity. Okay. You can apply a force F on it, on this mass. Okay, that's also applied. Now, what does this cam do? What it does, it's just rotating with an angular velocity, omega cam. Okay, theta dot. Now, the angular velocity is imposed on the cam by whatever prime mover that you are using. Now, based on the profile of the cam, if you open up the profile of the cam for a full circle from 0 to 2 pi, you will observe that the profile of the cam looks like this. Okay. I request you all to be punctual. Otherwise, it creates disturbance. Okay. So, if you open up the profile, it looks like this. You can plot it how the distance x1 is going to change for the follower based on the profile of the cam. And if you relate the rate of change of this deformation to the angle of the cam, you will get uh, this profile. And the slope of this partial derivative of x with respect to theta, that is the angle turn, that is actually the slope of this curve. Okay. Now you can see that x, this distance which is moved by the follower, is a function of the angle which is turned by this cam. Okay. So if you write it as the rate of change of this x1, that is the velocity, is actually equal to what? Because theta is implicitly dependent on time. So, and x1 is dependent on theta. So partial derivative of x with respect to theta multiplied by total derivative of theta with respect to time. And this we know is actually equal to the angular velocity of the cam. So you get this relationship v1 is equal to this partial derivative multiplied by omega cam. You see, this is actually the slope. This is actually the slope. And this slope is going to be different at different angles. So depending upon the angle that is turned at that particular instant of time, you will get a value of the slope that will have to be multiplied and you will get this. That means this is going to be a transformer, but this transformer is going to change because with angle, this is going to change. The slope is going to change. So we don't use a conventional TF, but we use a modulated transformer. That means it can change with respect to some other variable. So angular velocity of the cam is related to the linear velocity of the follower using this relationship. Okay. So the linear velocity is equal to this transformer modulus operating on angular velocity of the cam. Now, once you have the linear velocity of the follower, you can on the other side have the mass of the follower, which we have already discussed. You take the relative motion between these two because you see the spring and the damper across both of them. It's the same velocity difference. Okay, relative velocity. So you take the relative velocity between this. This relative velocity is V1 minus V. V1 minus V. So here you are making use of a zero junction because you want to take the relative velocity. You want to perform a difference. So you require a flow summing junction. So algebraic summation of flows takes place here at this junction. So this flow is equal to this flow minus this flow. It's available at this one junction. And it's common to both these elements, to the R and the K, to the stiffness and the damping element. So that's shown over here. Okay, so this is the model, complete model for the system. You can simulate this model and see for yourself how it's going to behave.